Part two of this lecture on section 6.2 is dedicated to this theorem 6.5, which is perhaps the most confusing theorem in the book. However, once we understand it, we'll see how we'll be able to use this theorem to generate a variety of random variables from a uniform random variable. So this theorem starts with our old friend u, the uniform 0, 1 random variable. Where it gets confusing is we introduce a function f of x, which is a sum cumulative distribution function, which we don't exactly specify which one, but it has the property that it has an inverse function, f inverse of u, defined for all u between 0 and 1. For example, this capital F could correspond to the exponential CDF, f of x, which is equal to 1 minus e to the minus lambda x for x greater than or equal to 0. To find this inverse, we set u equal to capital F of x, equal to 1 minus e to the minus lambda x. And now we solve for x as a function of u. And we obtain, for instance, 1 minus u is equal to e to the minus lambda x. And this implies by taking our logarithm that natural log of 1 minus u is equal to minus lambda x. And this implies x is equal to minus 1 over lambda, natural log of 1 minus u. And this is indeed the function f inverse of u. Going forward, we just want to think of this f inverse of u as some deterministic function, because now we're going to define a new random variable, and the new random variable is x, which is f inverse of u, but this u is capital U, the uniform 0, 1 random variable. Going back to our example, we have the continuous uniform 0, 1 random variable u, and we defined x is equal to f inverse of u. And for this example, where f was the exponential CDF that up here, then x is defined as equal to minus 1 over lambda, natural log of 1 minus u. And now here's the astonishing part of this theorem. This random variable x has a CDF, and the CDF of this random variable is exactly this function capital F. In the context of this theorem, this x equal to minus 1 over lambda log of 1 minus u is an exponential lambda random variable. What makes this theorem so useful is that computers are very good at generating random numbers, but the random numbers a computer generates model the case of uniform, continuous uniform 0, 1 random variables. And if you wanted to generate an exponential random variable or a sample of an exponential, then what you can do is you can generate a uniform u and then calculate this function log of 1 minus u divided by minus lambda. And the result is a sample of an exponential random variable. So my advice here is that you should use this theorem a few times before you read this proof. When you eventually dig into the proof, you'll see that the key is that this f inverse function is a non-decreasing function, and it's non-decreasing precisely because the CDF of which it's the inverse is also non-decreasing. So once you have that, um, you get the fact that, oh, the probability x is less than x, right? Is it probably f inverse of u is less than x? But that implies that u has to be less than or equal to f of x. But u is uniform 0, 1, and so this probability is indeed f of x. So this will probably seem circular the first 2 or 3 times you look at it, and so maybe go back to this later after you do a few examples. So this example is exactly the same as the example we worked before, but it just corresponds to the case where lambda is equal to 1. When you look at the solution on the next page, you'll see it's essentially just what we did. So here's a new example. We want to generate random variables x that have a uniform A-B distribution. So we need to define f of x to be a CDF of a uniform A to B random variable. And so we can remember that this CDF looks like the following. It starts at A and goes to B. It's 0, and it climbs like a ramp, and then it is 1. Algebraically, we have that f of x is equal to 0 for x less than a, and it's equal to x minus a over b minus a for x's between a and b. And you can check that this function is 0 at x equals a, and then it grows linearly, and then at x equals b, it's equal to 1. And then finally, it's 1 for x greater than b. And the key piece we're interested in is this piece right here, where we need to have the inverse of the CDF function. So to find the inverse function we define u equal to x minus a over b minus a, and that implies that x is equal to a plus b minus a times u. And this is equal to the f inverse of u function that we were looking for. And now the final step is we just simply define x equal to a plus b minus a times u. And this is precisely the g of u function that we were asked for up here in the problem statement. So this should make complete sense. If you want a random variable that's uniform from A to B, you start with one that's uniform from 0 to 1, and then you stretch it by a factor B minus A, and that gives you something that's uniform from 0 to B minus A, and then you add an A to shift it over to start over here at A. So here's the solution in the textbook, and uh, the only comment I want to make is that there is the alternate approach. You in 6.2.11 in that problem, like you could just simply start with a plus b minus a times u and simply derive what PDF you get from that using the methods we learned at the beginning of this section. And indeed, you'll learn that the random variable x then has to have the uniform from A to B PDF.